All right, we're at 7-1, day 1, and we arrive at a point where it is time to talk about an important new idea. The title of Chapter 7 is on sampling distributions. Okay? Now, we've talked about both of those parts separately, and it is a little bit like both of those concepts are getting put together. We talked a lot about distributions, right? They tell us how variables vary, right? What outcomes can they take on, and how often do they take them, right? Think of SOCs, shape, outlier, center, spread is how we describe them. Samples is where we just take a randomly selected small group of individuals out of our population to take a measurement. Sampling distributions tell you how those samples vary. Okay? Now we need to be good with some terminology here, because we got to get clear on the difference between a parameter and a statistic. A parameter is a measurement that comes from the population. This part of the definition is key. It is usually not known. Right? It is usually not known. It's just not possible to figure out what it is. Okay? A statistic comes from a sample. I like the letter association. That statistic, sample, parameters come from populations. Here's the ones you'll really need to know. Okay? Let's say that we're talking about means, because there's really, you'll see from here on out, for basically the next 4 chapters, we like to look at, are we talking about measuring a mean, or are we talking about measuring a proportion? And then, is it a parameter, or are you talking about a statistic? We have different notation for each one. For means, neither one's going to be new. We just haven't worried about keeping them straight. Looks like a big cursive U. It's a Greek letter, and it's pronounced mu. If you're talking about the population average, you say mu. Okay? If you're talking about a statistic or a mean that you got from a sample, we call that X bar. If it's a proportion, the parameter is just called P. The statistic is P hat. Again, you'd call that X bar, and that's P hat. So now those differences kind of become important. If you see a reference to mu or P, that's about parameters. Okay, X bar or P hat is a statistic. That would be a measurement that was taken from a sample. So here's kind of what sampling distributions do. Okay, we've talked about this idea before. Samples vary. Okay, we know that. We've talked about that. Here we're saying this question mark. Okay, that's mu, right? This sample right here is going to give us X bar. That's going to be our best estimate for what mu is. But what if we did it again? And again, and again. We won't actually do that, but sampling distributions take that into account if you did lots and lots of samples, so we kind of know how much variation we would get, right? We just take the question of how samples vary to the next level. Like so far we've addressed that they do. Okay, if you took the same population and took 2 different samples, you know that they would vary. Now we're into, okay, how much? How much variability would we expect? What kind of shape is that distribution going to take on? These kinds of things are what we get into. All right, in our first one, we're going to identify each of these 4 things. We just say that the population It's just 10-year-old boys. Okay. Parameter would be the third quartile of heights of 10-year-old boys, but don't know. Right? That's the point in taking the sample and getting a statistic, is that you don't know the parameter. Okay, you would have to get data on every single 10-year-old boy. Good luck with that. Okay, that's not going to be an easy thing to do, and that's why we would use a sample instead. Okay, the sample would be, let's see, the 50 boys in the SRS, and the statistic would be 56 inches. I should add to this, Q3 of all 10-year-old boys. Which again, that makes it kind of obvious that, yeah, that's unknown. Okay, that's unknown. Population. This one does specify it's in the U.S. So I'd say 17-year-olds. The parameter, we call that P, and as is usually the case, P is unknown, right? That would be the proportion of all 17-year-olds with a phone. Right, this number is probably a little low because this data is from 2012, but I kind of like that it's from 2012, because if you did questions like this day and age, the proportion would always be like 97, 98, or 99, or just some proportion that's crazy high. I kind of like that it's not a obnoxiously high proportion. Sample would be, let's see here, it doesn't say how many. It says when the sample was done. It's really, like I say, the sample of 17-year-olds that were taken, that led to a value for what we would call p hat, right? I have to call 0.71 p hat because that measurement came from the sample. If the sample was done well and selected randomly and all that stuff, it should be fairly close to what p is. In our iced tea example, sometimes we don't exactly know what the parameters, but here we know. You can think of it this way: if we have a number that we know we're aiming for, right? The bottle should have 20 ounces. Okay. Our quality control tells us from that sample we got an average of 19.6. Okay. Just like right here, total, we should, when we have all of the flights together, should be combined for 10%, but if you think of each flight as a sample, it's going to vary. So this particular sample, p hat, was 0.08. This is a nice little activity that you can do on your own if you want to start to build a sampling distribution. We'll do something like it in class, but it's a really easy thing to do if you have a deck of cards. We're just going to use the median instead of the mean. That's not often a measurement we're that interested in, but I just said to use the median with this one because it's easier and faster to calculate. But select, first of all, take out all your face cards, by the way. Take out your jacks, king, queen, and then take out all the aces. So you just have the numbered cards left. Draw 5 of them. And then just make note of what the median is. So I gave you a sample on here. If you got 2, 2, 4, 5, 9, the median would be 4, and on my dot plot I would go mark a 4, right? This is starting to get into how sampling distributions are built, right? If you think of it as a dot plot, those dots aren't individuals. Those dots represent samples of size 5, and we took the median of those 5. You could do this again, again, and again, and you'd be gradually building a sampling distribution. Good thing to do, right? You could just do it on your own, building a dot plot, super easy. Just draw 5 cards, take the median, and keep throwing dots on it. Okay, you'd eventually find that you would get something like this. Okay, that just has 500 of them, which leads to our first question. Is that the sampling distribution? And the answer is no. That has 500. So this would be like some computer software was used to do this. But if you did the thing with the cards, that's what you would expect to get, or something close to it. If you did the draw 5 and write down the median, 500 times. The actual sampling distribution has every possible sample of size 5. Okay? Usually when we have the actual sampling distribution, there's not a number associated with it because it's a crazy, crazy big number to think of factoring in every single sample. The graph looks to be symmetric. I'm down on part B now. Center's at about 6. Range looks to be 8. Doesn't appear to be any outliers. If you had a friend that did the same activity and said, hey, wait a minute, I got a median of 4, do you think they're using a different deck? Or were they doing it the same way you were? Well, they would be like right here. Right, our center was at 6. 4 doesn't seem like that crazy of a thing to get. It's just a little bit below the center, so I would say no. Getting a 4 is not too far off the actual median, so I would, if they got a 2, maybe that would be stronger. The farther you get away from the center, the stronger evidence you would have that maybe they weren't using the same deck as you. Okay, on the left, okay, what you have is data from different samples. Okay? Really simple question. Preferred color, blue or red? All right, as to what, those are your only 2 options, right? And we are looking at the proportion of people that said red. We think it's going to be right around 50, okay? But this shows 3 different samples. Here's a value of p hat that was 0.4. Here p hat was 0.55. Here p hat was 0.65, right? The sample size that they are using for each one of those is 20. So those have 3 separate samples of 20, okay? Each one of those turns into, like this right here, is 1 dot on the dot plot. Now there's lots more of them, but this first one would say, hey, put a dot at 0.4. But that's a huge thing with sampling distributions, is those dots that form it, those are from samples. Okay, we're used to seeing a distribution, and you think that those dots represent individuals. And now that's not the case. Okay, each dot represents a sample, and where it went on the number line is the measurement that we got. All right, I'm going to put together a little bar graph here about M&Ms with what they claim here, that you've got blue, like the proportion of each of these. You've got blue, orange, green, yellow, red, and brown. Okay? I'm going to say that these are percents. The individuals in this problem are pieces of candy. The variable I want to look at in the next couple slides are the percent that are orange. It does give me a parameter value here that if what they're saying is true, I'm going to say that P is 0.2. That's exactly where I'm headed here with my parameter. That's what a sampling distribution could test. You could take repeated samples, and it looks like the sample size we're going to use is going to be 5. But this distribution, or this bar graph here, is going to show parameters. So I'm expecting blue to be up at like 24. Orange should be up at 20. Notice the space I have between my bars. It's tempting to look at this and say, oh, that's a histogram. It's actually a bar graph. Okay? Remember, on a histogram, the bottom are like intervals of numbers, and then how many go in each of those intervals. Here, the bottom are categories. It means it's a bar graph, so my bar should have spaces between them. Green up to 16. Yellow to 14. Red 13. Brown 13. Okay? Those reflect parameters because I just took the numbers from what they said. Okay? So let's say we did a sample. Now I didn't actually do this, so I got to make up the numbers. But now I'm saying this is the number of candies, okay? Because it does give us a sample size of 50. I'm going to set this up the same way here and see we have blue, orange, green, yellow, and brown. Okay, so now I'm saying hypothetically, what could you see in a sample? So for blue, I'm actually just going to put in here what we would expect to see out of a sample of 50. So that's for blue, is I would take 50 times 0.24, right? Because you're expecting to get about 24%. So that's kind of the number out of 50 that I would be looking for, which would be 12. So let's say my sample does show that. And I got 12 blues. Okay, and again, that's for blue. Now for orange, I'd have to do 50 times 0.2, which would be 10. So that's really, for my parameter, that's the number I'd be looking for really closely, that if I were to do samples of 50 for orange, well, I'd measure all of them. But we should be getting about 10 of those 50. That would be our 20%. Green was 16, so I'm expecting a sample to give me about 8. Yellow, I think yellow was 14. So I'm expecting to get something in the ballpark of like 7 yellow. Now red and brown are a little interesting here, that if I'm going to think about this as an actual sample, I would expect about 6.5. But from a sample, I can't get 6.5. So it'd be like 6 or 7. And let's just say for red, to stay with those whole numbers, let's say red we get 7, and then let's say with brown we had 6. Okay, that could be a possible scenario of how the numbers would end up with the sample. So which of these would represent your sampling distribution? Okay, the bar graph on the left looks like data from a single sample, right? It's how many you got of each one. The two dot plots have this proportion where at least those could be sampling distributions, because each dot would represent a sample that was taken. Okay, and a sampling distribution should have data from lots and lots of different samples. Okay, they both look pretty similar, except they have one key difference. Is this is specifically for the proportion that were orange, and remember we had said that P was 0.2. So I do like over here that sampling distribution is centered at 0.2. Okay, and if the company's claim is true that 20% are orange, we should see that that's the case. All right, that and assuming that our sampling was done randomly, right, and we had good samples of 50, we should see some variability, right, because it didn't mean that we were going to get 10 orange candies in every sample, but that variability should be centered right around 20%. The middle one does, and the one on the right doesn't.